So we've been talking about sets, and on Monday we started talking about this idea of the cardinality of a set. So when our set has finitely many things, like for example this set has 3 elements in it, the cardinality of that set is just that number of elements. But when we let our sets get infinitely large, things get a little bit more complicated. So remember, infinity by itself is not a number. Right? Any number times 0 equals 0, but infinity times 0, I don't even know what that is. Another sort of paradox, if infinity were to be a number, we could take infinity times 3, and well, infinity times 3, I guess, sort of has to still be infinity. But the same thing holds for infinity times 2. Well, so then this implies that 3 equals 2. So something weird is happening. The general idea is that things go wrong when we try to treat infinity as a number and put it in place of a regular number in terms of algebra rules. We get paradoxes like this that just don't work. Right? Because of that, whenever we were working with a concept of something being infinitely long, infinitely large, infinitely far away, then we, at least in calculus, would often talk about it in terms of limits. We would never directly plug in infinity, but we would instead take a limit as something goes to infinity. And this is to avoid some technicalities for how exactly infinity functions. The point that I'm trying to make is that when we're talking about sets that are infinitely large, we have to be a little bit careful because our intuition about the size of something might be a little bit off if we try to use infinity as a number. On Monday, we also said that two sets have the same cardinality if there is some function that is between them that is onto and one-to-one. For finite sets, hopefully this makes sense. When we have sets that are different sizes, so we have A has 3 elements, whereas this B has 4 elements, it's not possible to come up with some function, to draw some arrows, that in this case hits every element of B. It's not possible to have an onto function no matter how we chose it. Similarly, in the second example, because our domain is larger than our codomain, it's not possible to have a one-to-one function. There have to be at least 2 arrows pointing to some element in the codomain. That said, if we had 2 sets that were the same size, 3 and 3, then it would be possible to find a function between them that is both one-to-one and onto. And so this logic applies to infinite sets as well. For example, the set of natural numbers and the set of integers end up really being, for all intents and purposes, the same size. So remember, the integers are numbers that look like 0, 1, 2, 3, etc., as well as -1, -2, etc. So all of the whole numbers that are either positive or negative, whereas the natural numbers are just the counting numbers 1, 2, 3, etc. So when we look at it this way, it looks like this set, the set of integers, is bigger than the set of natural numbers because, well, there's stuff included in the integers that's not included in the natural numbers. Right? The issue is that we're working with infinity, right? So in a sense, how much bigger is the integers? Well, it's twice as big, but twice infinity is still infinity. So our normal logic of, oh, well, it contains some things that the other one doesn't, therefore it's bigger, doesn't quite hold. Even though this set of integers has a ... on the left and on the right, sort of meaning that it's going off to infinity in both directions, we can actually just rearrange this integers to end up looking very similar to the set of natural numbers. Namely, if we start in the middle and then go right and then left and then right and then left, we can rewrite this set as 0, 1, -1, 2, -2, 3, etc. And then when it's written out like this, we can see that there is a function between the natural numbers and the integers. In other words, there's a way to line these up so that every element in the naturals is in a one-to-one and onto correspondence with the integers. Because of that, we really say that these two are the same size, or at least have the same cardinality. So if an infinite set can be ordered in the same way as this set of natural numbers, then we say that it is countably infinite. In other words, it has the same cardinality as the set of counting numbers, the natural numbers. So there actually are a lot of sets that have this same cardinality, that are countably infinite sets. And the question for today, or the question for this video, is, does this extend to the set of real numbers? So remember our sort of sets of numbers hierarchy. The natural numbers are a proper subset of the integers, which are a proper subset of the rationals, which are a proper subset of the reals. So does this pattern continue? Is the cardinality of the real numbers the same thing as the cardinality of the rational numbers? And as it turns out, the answer is no. There is no possible way of taking the set of real numbers and rearranging them and ordering them in a way so that they line up in a one-to-one correspondence with the set of natural counting numbers. This is Cantor's theorem. So up until now, we've talked about how the set of natural numbers has the same cardinality as the set of integers, as well as the set of rational numbers. Cantor's theorem is saying that this trend does not continue, that the set of real numbers has a different cardinality than these previous sets. Okay, so what does that mean? Well, one way of phrasing this, using our definition of cardinality, is that there is no function from the set of natural numbers to the set of real numbers that's onto and one-to-one. Put another way, there is no way of writing the real numbers in order and getting all of them. There's no way of listing out the entire set of real numbers. Thanks to the diagonalization argument, there was a way to take the set of rational numbers and put them in a certain order, and therefore to see how there's a function between the natural numbers and the rational numbers. This is saying it's not possible to find such an order for the real numbers. So here's the proof of this. Suppose there was a way of writing some order. Maybe we just haven't found it yet. There's a lot of different ways of ordering things. Maybe there's just some trick that we haven't seen. So let's give this the benefit of the doubt and say, hey, here we've got an order. Let's see if we get all of the real numbers. So over here I've written real numbers in their decimal notation. So we have 1/4, which can be written as 0.25, and then zeros from here on out. We've got pi in here somewhere. Any real number can be written out in this way. So the idea is, if we can list these real numbers out in order, then we can line this up with the set of natural numbers 1, 2, 3, etc. Unfortunately, this list, and any list, is doomed from the start. There's no way to write out the set of all real numbers in any order. Let's say a friend comes up to you and says, hey, I think Cantor was wrong. I think I found it. I found a way to write the set of real numbers in order. And they explain to you how they get their list. It's infinitely long, because there's infinitely many real numbers. And after looking at it, you say, I think you missed one. I think your infinitely long list is missing this number. Right? Here's how you come up with that number. Right. First off, I don't care about anything before the decimal points. We're only working with the component of the number that comes after it. So let's go ahead and start off with a 0. So 0 point something, and we're going to come up with an element that is not on this list. To do this, let's choose a first digit that's different than the first digit of the first element in the list. So anything other than 2 works. Let's just add 1. We want our second digit to be something different than 1. Let's just keep adding 1, and we're going to move down this diagonal. So 0.3228940. Okay. And this continues on forever. Notice that this number that we've come up with has to be different than the first element in this list because, hey, the decimal's different. It has to be different than the second number in this list because, hey, its second digit is different. So you say to your friend, hey, what about this number? Where is this number on your list? And no matter how far down the list you go, if you ever pointed to an entry in the list, maybe you're like, oh, well, did you try the 7th one? You say, no, I know it's different than the 7th one because it's got to have a different 7th decimal entry. So what we've done is we've taken an ordering, we've taken a list of real numbers, and we've identified a new real number. In other words, any list must necessarily be incomplete. So for this particular example, I went through and I added 1. You could have subtracted 1. You could have, at every step along the way, chosen any number, any digit between 0 and 9 that was different than the 1 in question. So we had a lot of choices for this. There's in fact a lot of numbers missing from this list. So since it isn't possible to list out the real numbers like we can with the natural numbers or the integers or the rational numbers, the cardinality of the set is different than the cardinality of the set of natural numbers. In essence, what we're saying is that there are actually multiple sizes of infinity. All of these sets are infinite, but this first group, the naturals, the integers, and the rationals, are somehow smaller. They're a smaller size of infinity than the reals and the complex numbers. Right? So to distinguish this, the terminology that we usually use is countably infinite versus uncountably infinite. There, however, are other notations. So the cardinality of the natural numbers is also known as aleph null. So this aleph, so in a sense, we've used all of our English Latin letters, we've used all of our Greek letters, so we're now moving on to Hebrew letters to designate things like cardinality for these infinite sets. So aleph null is the cardinality for the set of natural numbers. Analogously, the set of real numbers has cardinality 2 to the power of aleph null. So going back to when we started talking about power sets, when we first said that, hey, if we have a set that has finitely many elements, let's say it only has 3 elements, if we were counting the elements in the power set of A, as in if we were counting how many subsets there are in A, well, the number of elements in that power set ended up being 2 to the power of the number of elements in the set to begin with. So in this case, when we had 3 elements in a set, its power set had 8 elements. This 3 was an arbitrary choice. This could be any finite number n. And as it turns out, it doesn't necessarily have to be a finite number. The same type of logic applies to the cardinality of infinite sets. So the cardinality of the set of real numbers, as a consequence from Cantor's theorem, is 2 to the power of aleph naught because it's the same as the power sets of the set of natural numbers. I wanted to mention this notation with these alephs because I think it's interesting. But for the most part, if anybody's making a distinction between these different cardinalities, all they really care about is countable versus uncountable. Another name for this cardinality, the cardinality of the set of real numbers, is the cardinality of the continuum. And we call this because if we take some number line, so we have all of our real numbers, obviously this set has the cardinality of the set of all real numbers, but it's also the case that if we take any interval and talk about the set of numbers in that interval, the set of real numbers in that interval, the cardinality of this subset is going to be the same cardinality. Yeah. So I can actually choose any two numbers as close together as I want, let's say 0.001 and 0.0011, right? Two numbers that are very close to each other, arbitrarily close. The size of the set of numbers between them, the size of the set of real numbers between them, is this uncountably infinite set. So the cardinality of any continuous interval in the number line is the same as the cardinality of that whole number line. Right? Whenever we have all of the numbers between anything, that gives us the cardinality of the continuum. There are uncountably many real numbers in that interval. As I'm sure you can imagine, this procedure for taking power sets can be extrapolated. There aren't just two sizes of infinity, there are more sizes of infinity, maybe an infinite number of sizes of infinity, which I personally think is really interesting, but for most purposes, this distinction, countable versus uncountable, is really what matters. So if there's any takeaway from this video and the previous class, it should be that we have different sizes of infinity, and the main jump occurs when we're trying to go from rationals to reals.